Welcome to my first YouTube video. Today I will showcase some code I wrote to train a convolutional neural network to predict if an image is showcasing a sunny scenery or a rainy scenery. So it is about weather. And in this dataset there are 4 classes. And yeah, we will explore it right now, and then I will just showcase how to prepare the data in such a way that we can fit an actual model. And I think this is where many people struggle to actually understand how to structure the data so it can actually be processed by a network. So we start off with our usual suspects of imports. We have pandas and numpy to plot some images, matplotlib, and also CV2 of course, because we will use the images, and then some architecture for the networks. So the first step is I want to show you guys the data structure. So the images are in this folder, dataset2. I will also put the link in the description to download the dataset. And the images come in this form. So they have the label right here, then a number, and followed by the data format. And yeah, so we need to find a way how to extract the labels from the names. And essentially what we want to do is we want to create a for loop. We want to loop over every image, read the image in, so we have the actual array of pixels alongside with the label. And then this is why we need to find a way how to extract the label from this path name right here. And the first thing I did was to create a dictionary. So we have 4 classes: sunrise, cloudy, shine, and rain. And I just mapped them to integers because this is what our network will put out at the end as a prediction. This is the inverse of the dictionary, so it's just a list comprehension in a dictionary form. Just to reverse the dictionary to later on map it back. So the model's prediction we can map back to the actual label. And yeah, this is a useful function I found on GitHub to actually remove numbers from strings. It's a makeTrans function, and it just removes the digits with empty strings. To showcase how this one works, let's say we have our example image path. So this is what we will feed our process function later. So we have the path, and we want to extract only the cloudy. So first of all, we will take our example image right here and split it on the dot and take the first element. So if we split this thing on the dot, it will be separated, and then we will take the first thing. So we are left with this. Then we will split on the slash, so right here, and we will take the second thing because it starts at 0, right? So 0, 1. So we are left with this one. Let me just separate it as well. So we are left with the one in the middle. And then we use the translate function to remove the digits right here. And then we are left with only cloudy. So if I put it back together, as you can see, the output is cloudy. And yeah, I mean, we can do whatever, it will never change. So then we can use our dictionary to get the integer mapped and also the reverse. So this is a function we will use later on to actually get the labels for each image. So this is the processing function. I will just walk you through. So it will get an image, and the image will be read in by CV2 with the imRead function. This will create an array of pixels, and since we have colored images, we will have 3 channels. Then we will convert it to grayscale to save memory and also to have less computations. And this just happens with the CV color function. We pass the image we just read in, and then we will call color BGR because CV2 always reads images to in BGR instead of RGB, BGR to gray. So then we are left with the image height times image width, but only 1 channel. And then we will resize the image to have consistent shapes for our training data. And this happens by the cv.resize function. We pass the grayscale image, and then we pass a tuple of the image size you want. Obviously, if you use a larger image size, the training will take longer. But it can increase accuracy because the model can learn more nuances of the images. So this is how we prepare the actual image. So now to the label. This is exactly the line of code I showcased here. So it will output this string, and this string, as I also showcased here, will call the actual integer, which it is mapped to, and then we have our array of the image and our integer for the label. We will divide the array of the image by 255. Just real quick, we do this to normalize the values so the model can converge faster, and then we will return the resized image and the label. So this is our function to process one image. I can also just show that right here. So we call pre-process images, and then let's say let's pick this one. Also, I need to put, because we're not in this directory of the data set 2 and /. And as you guys can see, this is the array of the image, comma, and 1, because it is a cloudy image. Also, if we look into the actual image array, and we call shape, it's 150 times 150, one channel, so it's just width by height. And this is our resized image, which if we put 50 here, of course it will be 50. Okay, so so this is how we process each individual image. Now we need a function to iterate over our folder and do it with every image. So therefore, I first create two lists, one for the images, one for the labels. I would say for I in OS list the data set 2. So it's the same like this one, but now we iterate over it. Processed img and label img is the preprocessed images, and then we use os path.join to actually join dataset 2 with the image name. So this actually returns then the resized image and the label, and then we just append those two. So we append the images list by the processed image and the labels list by the label image, and then we return the arrays instead of lists. So I hope this makes sense. We iterate over the directory and pre-process the image. So then we call the function and we assign those two variables to it. So now we have, did I actually run it? Okay, so it's gonna run. It doesn't take too long. Image data, if I call now shape on it, we'll see we have 1123 pictures, which are of the shape 50 by 50. And yeah, this should be no surprise, but this is just the same number of observations, only one dimension though. So now we need to find a way to create train and test partitions to actually train the model and test it. And I actually use train, validation, and test. The reason why you should create 3 of those is to obviously train the network, validate it while the network is training, and then actually use some test data which the network has never been in touch before in any way to really avoid any knowledge spillover or leakage of the model. So we create those 6 lists right here, and then we actually zip those two together. So if I say if I use a list comprehension, say I for I in zip, and then those two, it will return a similar thingy as before. So it will return the image as an array and the according label, and then the next image as an array, according label, and so on. So we will iterate over this structure, and then we say random.random. So what is this? Random.random is just a random number between 0 and 1. And I can call this all the time again, and we will always get a random number. So if we want a split, for example, 90% training data and 10% validation data, we can say if the random number is above 10% or is above 0.1, then we will append our X train and Y train with the according image array and image label. If it is smaller than 0.1, then we can, for example, append the validation data. And I just did an else here because if it's smaller or equal to 0.1 but larger than 0.03, then we will append the validation data, and if it's even smaller than 0.03, then we will append the test data. So once again, I hope it's clear. So this one, if I put a 0 here, then I will only get the arrays of the images. And if I put a 1 here, I will only get the labels, because this is a zip, and I only iterate over it with one index. I can also say ij for ij. Then I need to put a tuple here. And then I can actually say, okay, append the X train with I and append the Y train with J. But yeah, I chose to do it this way. So you can just index the I for whatever you want. If you want the array of the image, and you get the 0. If you want the label, you put the 1. And this is what I do here. So I want to append the X train with the 0 because it's the actual array data, and I append the Y train with the 1 because this is the label data. And I do this for validation and test as well. Then I put a little assert here, because in the end I want the length of the X train to be equal of the length of the Y train, because then I know yeah, they're of the same length and it's nothing wrong. Alright, then I will return, just to be sure, because if you do deep learning and then machine learning, you always want to deal with arrays or the TensorFlow pendant. So I return all the arrays back. So this is what I do here. It's really quick. And yeah, so now we actually can already build our model. Let that sit here. So what I do is, or like the most important step is actually to get the input shape right. And yeah, what you want to do is you want to know how you resized your image. In this case, okay, I used 50 and 50. And this is why I need to put 50 and 50 here. We have only one channel because it's grayscale. So if you have colored images, you would put a 3 here because you have RGB channel. Now we only have a grayscale, so we have only per pixel only one value between 0 and 255. And I'm not going to go too much into that. Maybe it's interesting. It's pretty intuitive to explain the kernel, at least. So as you can see in this convolutional layers, we always pass a kernel parameter. So the kernel is actually just this window right here. So we have a 3x3 kernel right here, and this is a blurring kernel. So this is going to be used to blur an image. And what happens is, if you use a kernel, it will get put on the image like this. So this one will cover this light blue region, and then multiplications will take place, as you can see here. So we will multiply each of the kernel's values with the according value of the pixel. So in this case, we would multiply 105 times 0, 102 times -1, 100 times 0, and so on, 99 by 5. And once you add all this up, you will be left with one number, and this is going to be the value of the convoluted image. So all these values will add up to one number, and this is gonna be the pixel value for the new image. And afterwards, this whole kernel will shift one to the right. You can also set this parameter. It can also shift 3 or 5. Let's say 1, so it shifts 1 to the right, so this one will be light blue and this one will be black. So the kernel will sit right here and compute the value for this pixel right here, so for this one. And then it will go on to the right, down, and yeah, as you noticed, these will be lost. So these pixels will be lost because the kernel cannot go any further to the up left or up right, down left, down right. There are techniques to tackle that. You can pad the image with zeros. So you put zeros right here, zeros, 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 and then the kernel has some space to actually move there and compute this image. So you can say this as padding. Keras takes a padding parameter. If you say padding same, then it will return the same sized image. If you don't use any padding, then the convoluted image will be smaller than the input image, because as I said, those pixels will be lost. Anyways, to the actual model again. So we use 5x5 kernel with 48 filters to detect shapes in the image. We have the activation function value, and yeah, we have some max pooling layers as well. And in the end, important because we have a multiclass classification, we use the softmax activation function, and it will have 4 layers. So the last dense layer will have 4 units. 4 units, not layers. And yeah, so this is going to be our model. We initialize the model like this, and we also name the model with the current date. Well, actually the current time. So this is gonna, okay, let me import date time. Sorry guys. And then we will also set 2 parameters which are really important in the machine learning environment. So we have the early stopping. Early stopping will make sure that your model doesn't overfit, because it will stop the model's training after the validation loss, in this case, doesn't decrease further. And we will say the patience argument equals to 5. So if the validation loss does not decrease any further, we will train it for 5 more epochs until we actually stop the training. You can also put accuracy here and then max here. You can also put auto here, because it's really smart about if you put accuracy here, it will know to maximize the accuracy, and it will know to minimize the loss. So this is really important. Also, we use the Tensorboard callback to actually have a nice view on the model. Therefore, you need to create a log directory, and we will store the model as its name, and the name is the current time. So if you train a lot of models, you can compare it later in the Tensorboard. Actually, to call the Tensorboard, let me just do that real quick. Okay, projects. This is the virtual environment. If you never use virtual environments, I highly recommend it, because it will keep all your stuff clean. And then we will go into the weather directory and say Tensorboard log dir equals log. So now it will start up the Tensorboard, and then you can go to localhost 6006, and this is your Tensorboard. So later when we train a model, you can see some graphs here, which makes it pretty easy to compare stuff. And so those are the 2 callbacks we will use. After that, we need to compile the model. We use the Adam optimizer and the sparse categorical cross entropy. The difference between categorical cross entropy and sparse categorical cross entropy is actually the form in which you pass the label. So with the sparse categorical cross entropy, you can pass integers. So like those, you can just pass an integer. With the categorical cross entropy, you need to pass a vector. So then our sunrise would be something like this, and then our cloudy would be this. So this is just the calculation for the loss is the same, but or stays the same, but the shape of the label is different. For now, I didn't see a reason to actually change it. I can just change the loss function, and I'm good to go. So let me run those two cells. Now some reshaping needs to take place to actually get the X train and the Y train into the right order. So we reshape. Oh, again, I resize the images to 50. We reshape the images to the length of the actual data set. So our X train has 1003 examples in it. Each example is 50 by 50 and one channel. And the same with Y train. Y train will just be 1003 observations, and it will have a shape of 1 because it's just an integer. So this is required for the model to be able to fit it, and then we can already train the model. And yeah, once it finished training, I will come back to you guys and show you the Tensorboard. All right, so welcome back, and I opened up the Tensorboard to actually see what the model did. It stopped at 24, 25 epochs. And yeah, now you can see how powerful Tensorboard is. You can really do a lot. You can also see how the model is built up and what's actually happening. I'm actually, to be honest, not too familiar with this one, but you can, as I said, you can fit a lot of models and store them with different names, and then you can just compare them by clicking on them and comparing them. And yeah, you can see here the loss and the accuracy. It looks pretty okay to me. And yeah, we can see here now it starts overfitting. The validation loss gets much larger than the training loss. The model stopped, and that's what we want to see. So we reach an accuracy of let's say about 70%, 75 maybe. And yeah, so this was it for this video. If you have any questions regarding CNNs and if you have any questions regarding the video itself, let me know in the comments. And if you have any ideas on what to do next, if I should do a video and explain anything else, please let me know. Thanks for now, and have a good day. Bye bye.